Hey, Joyce.
Hi, Gerardo. Hope you're feeling better. At least you will be by tomorrow. All right. We started in our notes with a warm-up, and then we talked about life for a little bit, and then we're transitioning back. Anyway, hope you guys are good. And
Don't do drugs.
okay, don't do drugs?
Sometimes.
Okay. Math is better than drugs. All right, so solving differential equations. We already talked about separation of variables. We hadn't technically written it down. I don't really think there's much to write, so we just did an example. What did you guys do? How'd you properly separate?
I divided y, or y multiplied dx over. Leave the 4.
Like that?
Can't we leave the 4?
That's a horrible integral.
No, we can't. Never mind.
No, because
totally
we have to keep it grouped together, otherwise we're in serious trouble.
Yeah, I just realized that.
Struggle, huh? But now we can go ahead and, if this is all that he was, we'd be doing all right. So, anyway.
Integral stands for.
You guys use ln's, right? And we can go straight to ln of y plus 4 because if u was y plus 4, what's true with du? Sweet. That's an easy substitution. On the other side, we have ln of x plus e. Uh-oh. How do we get rid of stuff? E to the. And then we end up with absolute value of y plus 4, absolute value equals c, e to the ln of absolute value of x. Question, why can we kind of take out the absolute value?
Because the c absorbs the negative.
The c kind of absorbs the positive negative possibility, which might mean that for a different initial condition, the c might be a different value, like have a different sign, just something to be aware of. But if they give us an initial condition, we'll find the right c, and so we'll be okay. We'll end up with y plus 4 is equal to c. Uh-oh, what's left now?
E to the f.
E to the ln. What happens? Boop, that's gone. Why can I kind of get rid of that absolute value yet again?
Because the c absorbs
The c can absorb the plus or minus again. So then we can end up with y is equal to cx minus 4. Dun, dun, dun. Aha! What is the only way that we would be able to fill in c?
No y and x.
If they gave us some sort of particular x, y. True?
If they
Alright.
give us x, would we be able to find y?
No.
Alright, so we have to give them both.
Yeah, they'd have to give us an entire point. Okay, so anything new or unique or interesting about this one?
Yeah.
Not really, because if they give us some sort of y prime, then we'd have to do dy dx, right? I'm not going to actually solve this whole thing. Just our separation practice, we have y dy equals 2x dx. No ln's on this one, nothing crazy on this one. It'd just be solving, but no initial condition. We'll still have a c at the end, and we'll carefully show our work step by step. True? So then, whoop, what's so special about this differential equation? dy dt is equal to k times y. Why does he have his own little deal? And to be honest, kind of his own little section.
He's a gangster.
Because proportional growth, or a rate of growth that is proportional to the amount that you have, is called exponential growth and decay, and it is modeled, it is shown, it is seen in many different ways, many different places, many different applications, from money and finances and interests to radioactive decay. Someone's keys, to bacteria growth, population growth. It's a big one. And technically, our book has certain examples where you don't necessarily have to keep the growth with an exponential of e. Sometimes you can make different bases based on the growth that you have, which is kind of interesting. We're not going to go too crazy into that though, because frankly, we don't need to be honest, for our applications. But wait a minute. Why do I say proportional and then inversely proportional, and then I only show directly proportional below?
Because k can be either negative or positive.
Yeah, k can be either positive or negative. The proportional would just be ky dy dt. Where k is positive and inversely proportional would be dy dt is equal to negative ky, where k is negative.
It's d.
Yeah.
I think I remember something about last year. It was like proportional meant ky, and then inversely proportional was k over y. am I
You're
thinking
thinking back to algebra.
of? Okay.
Long story short, when we integrate, since we're talking about rates and we're not talking about amounts. If we're talking about amounts, then we would say k times y and k over y. But since we're talking about rates, the negative has the same effect as, in a sense, division of an amount. And I'll try to show that. I'll try to show that. Okay. So what happens when we try to integrate by separation of variables, or solve, I should say, by separation of variables, the proportional equation? Wait, what? Where does this come from? That makes no sense. Well, kind of it does, right? Because how do we separate the variables?
Divide y, multiply dy dt.
So we have our dt instead of our x, right? Then we have our ln of absolute value of y is equal to kt plus c, and then we have our e per group, and then our e per group, and then we have y is equal to, remember the absolute value is absorbed by the plus or minus possibilities of c. And then if k is positive, that's growth. Hopefully, obviously, because a positive exponent is going to indicate the number is growing, and then if k is negative, that indicates decay. Because a negative exponent is the same thing as 1 over, hence the division, kind of tying back to what we were saying with directly proportional and inversely proportional. Long story short, inversely proportional just means as one grows, the other one decreases. So if you think of it as 1 over, as k grows, the entire number decreases. So maybe that helps a little bit in the sense of decay as time passes. The amount is decreasing, hence the inverse relationship. So then that kind of leads us up to this little theorem. I don't know if it's necessarily explicitly stated as a theorem in our book. It was in last year's book. And I don't necessarily know if you need to write it down, because we've already written down that the rate is directly proportional to the amount. And this is kind of an interesting idea because the more that you have, the faster it grows, and the less that you have, the slower it grows. That's kind of interesting. Or the more that you have, the faster it decays, and the less that you have, the slower it decays. That's kind of interesting as well. Thinking about exponential, how it kind of evens out as you go to the left, or grows faster as you go to the right. But either way, you end up with this final exponential growth equation. Hopefully we know that c is the initial value, because when t equals 0, this whole thing is 1, so therefore y equals c must be the initial, or the amount when t equals 0. K we could call a rate. That's maybe a little bit too simplified. The proportionality constant's a little bit more general. And then we already talked about growth happens when k is positive, decay happens when k is negative. Are we good?
What is so K and C are both constants, right?
Yeah, k and c are both constants. This one denotes the initial, and this one denotes basically, in some senses, the rate of growth, or the rate of decay. Okay, so that just got exciting. How do we solve this exponential growth model? The rate of change of y is proportional to y. Wasn't that just exponential growth?
Yeah.
When t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of y when t equals 3?
And if that's the initial value,
Yeah. So you basically say, okay, the rate of change directly proportional to y. Can't we skip a few steps? Not that we would in the AP, but we can skip ahead and say, oh, hey, isn't that just exponential growth? How do we know it's growth? That says growth, but what else happens?
positive.
As t grew, what else grew?
Y.
Yeah, so it's growing, not decaying. So we know that k is going to be positive.
We actually have to integrate on the AP.
They usually give you ones that aren't quite as simple. So hence, integration is still necessary. But in like physics, the exponential growth model is super common and it's used for a lot of different applications, so you just kind of have to memorize it. Plus, in a lot of physics classes, non-calculus-based physics, they wouldn't necessarily have you integrating things, sadly. Calculus-based physics, though, they'll get more interesting. They would say something like, this involves some calculus that most of you wouldn't be able to do, so let's move on and memorize this formula. And you're like, oh, great. And then you do the calculus and you're like, I get it. Okay, so how do we solve?
So we have to find C, but C is 2. When T equals 0.
We have two unknowns, and how many clues do we have?
2.
Oh! Can we
No.
just plug in and set the system of equations and solve?
Oh.
Come on, mathy ones. So therefore,
Why don't we
you're
use
right,
like
t equals 0, so therefore we can go straight to?
Yeah. C
Alright,
equals
we'll go straight. So we know that you could plug in t is 0, right? That would just be 1, and then
And then
y
we
is
have to
2,
find
so
k.
c is 2.
So 2C or 2E, and then we have to find K. So
Now we can plug and check our other clue, right?
yes.
So then y is equal to 4.
2E, so 4K, or 2K, and divide by 2. Yeah, I want to divide by 2.
Let's go for it, right? Better safe than sorry. So ln, that cancels. K is equal to 1/2 ln of 2.
So I'm going to do 2.
Technically, some books would have you memorize that K is equal to, and they would say, hey, whenever the amount doubles, doubling in half-life, whenever the amount doubles, you can call that something special and memorize, but we don't need that. Now we have K, and so all we're going to do is plug and check. We have our 1/2 ln of 2 times 3.
And then that's our answer. Stick it to the man.
Sure? Can you do any better than that, though? Without a calculator?
Yeah, bring the 1/2 up.
We're not bringing the 3/2 up.
Oh yeah, bring that up.
Because the 3 would be times the 1/2, so then the 3/2, and then e to the ln.
And
Then we would have
so 2 times 2 times root, so 4 root 2.
we either do 2 to the 5/2. Why? We have a 1 plus 3/2. Or we can make it super snazzy and say it's going to be 4 root 2. Either way. Because that's 2 to the 2.5, and 2 squared is 4, and then the 1/2 is 4. Sorry, it's square root of 2. Does that work?
What is it? No.
That was fun, right? That was just simple math.
No, it's not.
So what about this one?
Half-life? No, it's not. What is?
The rate of decomposition of radioactive radium is proportional to the amount present at any time. The half-life of radioactive radium is 1,599 years. What percent of a present amount will remain after 50 years?
So 2 equals e to the 50K? Is that too simple?
So we can still say, hey, since it's proportional, we can use our exponential growth decay model, right?
Oh, but it's negative. Right?
Well, it is going to be negative, but aren't we going to hopefully figure it out to be negative on our own?
Yeah.
Okay, but we know that k should be negative eventually, or a negative number.
So then half-life would mean it's 2. 2 equals e to the 50K. Because t equals 50.
But why is half-life 2?
Because we don't need.
What about the
Defines-
1599?
What?
What about him? Does it make a difference?
Yeah. Or different.
But isn't it, no matter what we do, the y is going to end up equaling 2 when we start solving? Because we have to divide c over. And theoretically, c should be double or half of whatever.
Can we do that?
Yes.
Does that make sense?
But then we're finding k
Uh-huh.
at that time, and then we'll
Uh-huh.
plug in k to the
Because we can say that whatever amount you have, it doesn't matter how much you started with. Whatever amount you have with a ratio of what amount you started with is going to be 1/2 for the half-life. So I can use that trick. Half-life is a time when y is equal to 1/2 c. Could do it that way too. ln both sides to find k. Divide by 1599, so we'd have ln 1/2, which ends up being a negative. Really?
Yes.
Mm-hmm. Because ln, right? Doesn't he have an intercept usually at 1? So therefore, 1/2, that is a negative. So our k is negative, hence it denotes to k. Does that make sense?
Then we have to find.
Ooh, a percent. We can plug this in, right? C e to the, and we have 1/1599 ln of 1 half times. We can plug in our t of 50 years,
And then just whatever number times 100, or is it just that whatever number?
but how do I get a percent?
So we know it equals. Cause C we can. Is it 1/2, right? If you divide the C over, it's gonna be.
Ooh, if you divide the c, where are we dividing if we need a percent?
Because we need to solve for.
Solve for the ratio of how much we have to how much we began. For instance, over here, when we divided by c up here in this original equation, weren't we figuring out percent? 1/2 is 0.5 and 0.5 is 50%, so when 50% is left. So technically the ratio of what you have to what you started with, this denotes not the percent, but we can find the percent, right? So when the ratio, when the percent, we're solving for the percent, never mind. We're solving for the ratio. So y over c is equal to, we could do 50/1599. We could just plug and chug this to our calculator, I suppose. Let's just plug and chug it. Because it's not going to be pretty even if we do the 50 times 1. The 50 divided by 1599 anyway. What do we get? Oh, I've trained you too well. No one has a calculator. And that doesn't have ease. Amanda, you've got it, right? But no one's backing her up. Okay.
Calculators are for.
Yeah, I just don't ever have my calculator anymore.
I want to take it home when we're doing stuff like this. Like when we were doing derivatives, I was like, no.
I'm like, man, okay.
I'm just double checking.
No test.
Put test big gold question mark and put it on this. Why? November. 0.978? 0.979. Although for being super snazzy, 97.856%. Whoa! There's a lot of it still left after 50 years.
Because the half-life is 15.
Yeah, that makes sense, right?
Yeah.
Alright, cool kids. Anything else? Boop. Ooh!
Newton.
Newton's law of cooling.
Newt.
Something else from physics. Now this is a little different because if you notice the differential equation isn't quite ky. Newton's law of cooling, you're going to need it on, I think I only gave you one homework problem with him though. He's probably in your book too if you want to look back. But differential equation. Uh-oh. What's capital T temperature? What's little t time? What's T sub S? What's T sub 0?
Is it T sub naught? No.
T sub naught would be the initial, right?
And then so T sub S would be the final? No. You usually do final minus initial, don't you? Not initial minus final. I don't know.
What is T sub S? Actually, I have no idea. Let me read you a snippet.
Snippet.
Snippet. It's not one we have to memorize, which is why it's not like in a nice, spiffy, cool, like boxy thing. Ooh! Okay. Capital T is the temperature of the object at any time, little t. T sub S is the surrounding temperature of the environment that it's in, and T sub naught is its initial temperature. That makes sense. So, what do we have for the problem at hand?
Who uses Fahrenheit? We should use Kelvin.
Just 'cause.
Because it's science. Science uses Kelvin.
Mhm. What water temperature in Fahrenheit, whose room temperature is kept at a constant. That's our T sub S, right? That's the surrounding temperature.
Is
The
that
object
actual-
cools from 100, to 90, T at T. Oh no, T at 10. Dun, dun, dun. How much longer will it take for its temperature to decrease to 80 degrees? That would be T sub some sort of specific T.
T sub T at T such that I have no idea. T capital T equals 80.
Find T when T equals 80. Ah, there we go. Okay, so what can we do? Could we integrate and be snazzy and be like, haha, I know why that's true. I suppose.
We know it's true.
But we'll just say we know it's true for right now, because we're not going to be asked to prove that we saw cooling on the AP exam. So therefore, what do we know? T minus 60 is equal to T sub naught would be 100, minus 60 would be the room temperature. That's how many degrees it needs to cool, right? Or it can cool. Because you're going to cool to room temperature and then stop cooling. E to the negative K times, okay, hold on. This is our main formula, right? We could say T of little t is equal to 40 e to the negative k times t plus 60. Okay. Now how do we use that?
What happened to our T? Our big T.
Or which t?
Our big T. Capital T.
He's
T
still
minus
there.
60.
I just made him like a little function you did.
Don't we have to subtract T over?
Well, he's kind of like our y though, because he's the current temperature.
Okay.
So like for instance, I'm going to go ahead and plug in, right, for our clue. T of 10 minutes passing is going to be 90 degrees. That's after 10 minutes. Haha! So I'm going to solve for k. So I can subtract 60, that's 30, and divide by 40, that's 3/4. ln it, so negative 1, 10, ln of 3/4 equals 0. How's that look?
If we do from the top one, or do we have 20 equals 20 equals 40 e to the negative kt?
20 or 30?
Because 80 minus 60.
90. We're not doing 80 yet.
Oh, we're not playing it.
Yeah, 80 is our final. Our clue is, remember, our clue is the one that we know, and the one that we know is after 10 minutes, 90 degrees. So all I have to do is plug and chug and, set t equal to 80. All right, so it's a little bit exciting, but not so much. End up with 40 e to the negative 10 to negative is a positive, so 1, 10 ln of 3/4 times the t I don't know. Plus 60, right? You guys are all double checking my math?
How did you lose the negative from 110?
Because I plugged him in, and he was a negative.
Oh,
Does that make sense? Because the negative was denoting decay, but the ln of 3/4 is already negative, so then I don't need when I plug back in. Subtract the 60 as 20 divided by 40 is 1/2. ln of 1/2 gets rid of the e.
Oh, sorry, Miss T. How did you do 1/2 again?
Minus the 60 divided by the 40. There you go. And then I'm taking ln of both sides, and that's what lets me get rid of the e and then ln of 1/2. So I get my 110. Okay. You guys catch up and then
And
we'll
you
see.
put the 10 on top, right?
You can, yeah. I'm just being a total lazy bum and not wanting to make any mistakes.
Smart. Because I know I
Make
can make
little-
those little mistakes
Yeah, right?
a lot.
Like the poor little A beers that went to go make an equation of tangent line and made it wrong when they tried to simplify. And they could have stuck it to the man.
Yep, always do.
Box.
You guys agree with the math that worked out?
Yeah.
24.094. So kiddos, you're gonna have a few. I try not to give you too many, but you're gonna have a few application problems where you're not necessarily integrating, but you could be integrating because it actually all goes back to, hold on, minutes. A differential equation that's being solved in order to get the relationship that we then use to solve. So I gave you a couple just to have you play around with, having information, plugging and chugging and solving accordingly. But the main point of section 7.4, for me anyway, is solving differential equations and plugging in where necessary. Sound good? Sweet. Back to your spirals. Let's go back and pick up that FRQ. Now that we've talked a lot about separation of variables. There we go. That we didn't get to do before. Huh. You know what? There's too much going on this page. Let me clone the page. Let me erase all the extra stuff that's in our way. There we go. Let me zoom over here to our free response. Okay. Let me move it down. If you guys have test corrections to turn in today, if you didn't get them turned in earlier, due by the end of the day, you guys know what to do. Ready, set, let's finish it off with our Furquois. You're welcome. It's French, like Target. Or maybe it's German, like Walmart. Some of those other spiffy high-end stores. Although Target is better than Walmart. For most things.
You would just have to like, for A, you would just have to draw it on the slope field.
Yeah, just don't draw the slope field, just sketch me what it would look like the one that you would sketch. Does that make sense? Just a single solution. We'll have stamp sheets due by the end of the week. So if we need to make them up, or need to make up one, go and get it in so that your beaters are slacking. But if you don't need to, it's a free week, hence the tutoring hours instead. Sound good? Mm-hmm.
Are we gonna have another stamp sheet?
We'll start one next week.
For B, can it be anything?
Can it?
Is it with the given points of the honesty? 0, 1, and 0.
Well, the given differential equation.
Okay.
Oh, that's asking for Y.
Is a solution. Ish, right?
Wouldn't the first one be a line?
Yeah, I thought the first one was a line.
Was it? Did I not see it clearly enough?
Because it's just through that point, so.
Oh, yeah, you're right. Good call. I didn't see it. What would it take to be a solution to a differential equation? Is that what we're on? This is very similar to an FRQ a couple years ago. some people were like, "Ooh, we have to solve by separation of variables." But the problem is, if you multiply by dx, is there any way to separate the y and the x?
I'm confused.
Some people thought they had to solve for y. So then they were like, "Why didn't you teach us how to solve when there is addition or subtraction?" The problem is, you can't. Separation of variables breaks down. It doesn't work. Because we can't divide by y, because then it would be 4x over y, and y isn't truly to the other side. We can't subtract, or else we're illegal because we're subtracting a dx component. So they don't actually ask us to solve, so what on earth can we do?
Use it.
Yeah, how do we use y equals 2x plus b in the differential equation though?
Plug in that for y, so we have 4x plus 4b minus 4x. So then we have.
Okay, we could, right? So 2 times y would be 2 times 2x plus b minus 4x equals dy dx, but does that get me all the way?
Because dy dx equals b.
Not b,
Or 2b, my bad.
not 2b. What does the differential equation solve for in a line?
So,
Doesn't it have to equal 2? Does that make sense? Because you can either think of the slope of the line, or you can think of what's the derivative. Well, either way, it gets you to 2. Don't I need the derivatives to match up? Does that make sense?
we're solving for b.
Uh-huh.
So b equals 1.
Justify your answer. I don't like how they put that. They wouldn't have asked you to justify your answer. They would have said something like, show the work leading to the solution. But basically, long story short, in the beginning, since y equals 2x plus b and y prime is equal to 2, which must equal dy dx at or for this solution, simple plugging and chugging gets us all the way, right? So I don't like them saying justify. We'll say instead, show the work that leads to the answer. Does that make sense? But they tricked so many, because so many that year thought you actually had to solve that. That was Danny Regan's year. Letter C. Let g be the function that satisfies the given differential equation with the initial condition g of 0 equals 0. Oh, it's a point now? Initial condition 0, 0, wouldn't that be here? It appears from the slope field that g has a local maximum at the point 0, 0. Using the differential equation, prove analytically this is so, aka algebraically. Ooh, how can we prove there's a max?
Concavity. Or, no, increasing to decreasing. No?
But that's not analytically, that'd be just looking at the graph. So if it said something like
You
demonstrate.
could, like, do test points with a sine chart.
Yeah, we could do a sign chart, but of what?
dy
First derivative?
dx.
No, don't you have to find dy squared over d squared?
We have to use second derivative test. That's the only way to prove it,
That shows concavity though.
True, but remember it can also show relative extrema if we plug in a critical number. It's a critical number because the first derivative is 0, right? So we can say at x equals 0 or at 0, 0, our original function g has a critical number, but that's not enough. I'm going to go ahead and find the second derivative, which would be 2 dy dx. Can I just plug in dy dx? Is that okay? Minus 4. So 2 dy dx. I plugged in 2y minus 4x for dy dx minus 4. So what would be my second derivative at 0, 0? Now it's time for us to plug in each other, right? And the reason we're doing this is because anything else would be experimental, and that wouldn't be definite. But if I plug in 0, 0, don't I get negative 4?
Why did you plug in dy dx? Because you have to use the
how do I put those clues together? Since G has a Negative indicates that G is concave down. If G is concave down and has a critical number, what must that relative extrema be?
No.
That would be, let's say, by the second derivative. Alright, cool kids, we're good. I just wanted to do this one because as you guys learn more and more simple differential equations, you might look at that and think you have to solve, but no, they did not ask us to in this one. Alright, cool kids. Section 7.4. How to attempt for smaller piece, and we'll grade it quick and make sure you guys are good. So, nice thing is only some calculus tonight, right? Some plugging and chugging. Have fun. Bye, Joyce. Bye, Jordan.